All right, so the last speaker of today, Stefano Pagliarani, will talk about heat kernel estimates for SDEs with singular drift. Please go ahead.
Okay, so thank you everyone. So I'm gonna try, so I'm the last talk of the day. Everyone must be pretty tired. So I'm gonna try to keep it light. So don't get scared. I don't have 22 slides. It's only, most of it, many of them is bibliography. So it's only 15 slides. And so it won't be too heavy, I hope. The topic is a little bit technical, but I tried in this presentation, which by the way is the first time I present this. So, and I tried to put the focus more on the concepts than on the technical aspects. So let's see how it goes. So today I want to talk to you about some recent developments in the world of heat kernel estimates for SDEs, Brownian SDEs. In particular, I would like to present to you some new density estimates for SDEs with singular drift. Okay, so the way this, first of all, this is a joint work with Stéphane Menozzi from University of Évry. The way so in the paper, which is not yet on the archive, it will be probably in about a week or 10 days, something like this. We considered mostly the degenerate case, the case of degenerate diffusion, degenerate noise. And then we had as a corollary the same results for the non-degenerate case, okay, the case with if you want, with elliptic diffusion. However, in this presentation, so of course in the paper it made sense to do it like that because one result is more general, but in this presentation I would like to keep the focus on the singular aspect and keep the focus away from the degenerate noise aspect. So I will do it the other way around. I will talk first about the non-degenerate noise, which is a particular case. In the last 3 slides, I will try to give you the full picture. Okay, so we start in the non-degenerate setting, and we start by reviewing a little bit what we know about heat kernels for standard SDEs, let's say, when SDEs with non-singular drift. Okay, so you can consider a very simple stochastic differential equation where you have a drift term, F, and a diffusion sigma. And then I'm going to start right away with some assumptions, okay? Because to derive density estimates, you need assumptions. So right away, we ask an ellipticity assumption on the diffusion. So the sigma, this is a scalar SDE for simplicity. So the sigma will be strictly positive, bounded away from 0. And we're going to have also some Hölder regularity for sigma. Okay, this shouldn't be surprising. So we assume sigma to be C Ni. This is a standard Hölder space, so nothing difficult. In particular, sigma is bounded. The assumption of F is slightly more complex because we're still in a Hölder space. However, there are 2 things that should be highlighted. The first one is that this regularity coefficient gamma could possibly be 0. Okay, when the regularity coefficient is 0, it means that this function f has no regularity except for measurability. It's only measurable and with sublinear growth. Okay, so this is a slightly different Hölder space because it's not, it doesn't imply that this function is bounded. Okay, this is an additional complexity that is added in this paper that I'm presenting. If you want, you can consider this f also bounded, and in this case, many arguments will be simplified. Okay, I will try to show you what are the simplifications that can occur when this f is bounded. Okay, so as I said, it's only for notational simplicity that we assume x to be scalar valued. And also only for notational simplicity that sigma and f are time independent. Okay, in general, you can take them, have the coefficients to be functions of time. And the assumption that is written here will be replaced by these. So basically you want the Hölder norm of sigma and the semi-norm of f to be bounded uniformly in time. Okay. So in this setting, which is, as I said, quite standard, but not completely trivial, because this the function, the drift f can be unbounded and non-regular. There are some existing results. So when it comes to the study of the stochastic differential equation, we have weak well-posedness. So in the sense that you can prove, it has been proved, existence and uniqueness for the martingale problem. And here by martingale problem, I mean the standard Strook-Varadhan martingale problem. And then there are some density estimates, so heat kernels, which I divide here in the slide in two types. So the Aronson type bounds, which tell you this. So we denote like this the transition density, okay, of the solution. So the transition is from the backward variables Sx to the forward variables. And we have a Gaussian lower and upper bound. So both sides, you have a Gaussian function density that bound as a bound. So maybe we can start. So here, so you see the G lambda is basically a Gaussian density with variance lambda times the time. Okay, this is not surprising. Lambda has to be, of course, a constant that is big enough. The constant lambda as well as the constant c will depend on a finite time horizon and all the assumptions, so the constants that appear in the assumptions. And you see the Gaussian is shifted, so the mean of the Gaussian is not simply x, but it's theta of x. Okay, what is theta? It's written here. Theta is any flow associated to the drift f. Okay, the necessity for having a flow here, in usual standard Aronson type bounds, you have simply x. The drift is typically bounded, but here we are taking f unbounded. So in a way, you have to keep track of the. You need this flow here because this the average, the expectation, and the Gaussian bound has to keep track of the drift of the process. Okay, which is unbounded. So a few simplifications, as I said. So if f is bounded, then you have a usual Aronson type estimate. So you can get rid of the flow and simply put the backward variable, x. And also, this is a bit more technical, but so the concentration constant, that's how I call the lambda that appears here and here, becomes independent on the time horizon. C does never become independent on the time horizon. Okay, so this is something important to keep in mind, especially for whoever is interested in studying the long time behavior of the solution. So these estimates, this type of estimates, are naturally proved up to a fixed time horizon. Okay, so I'll be back on this a bit later because, okay, this is something I haven't mentioned. So this paper that I'm presenting is not strictly related to Libera in the sense that University of Évry is not within the network. However, the results I'm presenting today might be useful for an ongoing project with Jonas Tulle, which is indeed a project within Libera. Okay, I will say a few words about that later. So these type of results are standards up to some extent, as I said. So the important one here, the one that we're using the one that is written here was specifically obtained by Menozzi and his co-authors, including Antonello Pesce, who's in the audience, or at least he was up to a few minutes ago.
Yeah, I am.
Okay, great. And so we're going to rely strongly on these results, on these estimates for the singular case. So these were the Aronson type bounds. And then we have what I call the regularity bounds, which I subdivide into categories, those in the backward variables. So in the backward variables, we have a uniform bound, a pointwise bound for the gradient. Okay, the gradient. So I'm used to, I know I said we're in dimension 1, but I'm used to call it a gradient because actually in the paper we do everything multi-dimension. So allow me to call it this, the gradient. It's a bound on the gradient in the backward variable, and you can see the usual trade-off between regularity and singularity. So the gradient weighs like the bound on the gradient translates into a singularity of order 1/2. Okay, and again the bound is uniform because we can bound uniformly in all the variables with this Gaussian, and you see the flow always appear here. So furthermore we have some Holder regularity for the gradient. So what is expected? Well, the drift, the coefficient which is less regular is f, which is C0. The equation regularizes by 2, almost by 2, so you expect a solution which is almost C2. Indeed, we can prove, it's been proved that the gradient enjoys Holder regularity for any eta between 0 and 1. Eta b stands for backward here. And so this is the estimate you obtain, simple Holder estimate. You can see the usual scaling here. So for a regularity result of order 1 plus eta, you pay 1 plus beta halves of singularity. And here, as usual in this setting, you need to bound with 2 Gaussians, not only one centered at one point and the other centered at the second point. This summation here is because these estimates want to be uniform in time and space. Okay, so you need something uniform in space, and x and x prime may be very different from each other, very, very far from each other. So a few remarks. So if the drift is actually Holder, so if gamma is strictly greater than 0, then you have C2 plus gamma regularity as expected. So then you will also have a bound on the second order derivatives, which in particular tells you that the solutions to the Kolmogorov PD will be classical solutions. And also you will have eta Holder regularity for the second order derivatives. Okay, so this is pretty much what is known in the backward variables. Concerning regularity in the forward variables, well, then this result was not contained in previous articles, in previous literature, so we had to prove it from scratch, using, however, the same techniques that were used in the paper by Stéphane, Antonello, and their co-authors. So the missing estimate that we needed was this one in the forward variable. So here delta can be, this delta, which is colored in blue, can be either 0 or 1, meaning that this Holder regularity is for either the density, the transition density, or its gradient in the backward variable. But the increment here is in the forward variable. I'll try as much as possible to keep blue for backward variables and red for forward variables to make the reading easier. And you can see the again, we have a bit of Hölder regularity in the forward variables. The singularity here is the one you expect, the usual. And let's have a look at the threshold. The threshold here is ni. Okay, ni was the regularity of the diffusion. Okay, I'm going back quickly to the assumptions. So sigma is ni Hölder continuous. So in the forward variable, you can only expect ni Hölder regularity. What is the intuition about this? Okay, this is not a proof, but it's just a hand-wavy argument. So you can think that P, or its gradient in the backward variables, will solve the Fokker-Planck PD, okay? Because in X, in the Y variable, okay? Because in X, the density solves the Kolmogorov PD, but in Y, it solves the Fokker-Planck PD. Now, the Fokker-Planck PD moves two derivatives on the diffusion coefficient and one derivative on the drift coefficient. Okay, so according to this reasoning, you have the Fokker-Planck PD will have a diffusion coefficient which is of class ni minus 2 and a drift of class gamma minus 1. Now, clearly, the worst one here is this one, ni minus 2. The PD regularizes by 2, almost, and so you end up with a solution which is in C ni minus, okay? Something smaller than C ni. Okay, so this is the idea, nothing unexpected. It's just to prove this, because of the business with the flows, it's quite complex, quite technical, but nothing morally unexpected. Okay, so of course, in the forward variable, you have no derivatives in Y. Okay, before we move to the distributional drift, is there any question so far? Okay. So I'm gonna move on to the case of distributional drift. So now we consider the idea behind this work is to consider a perturbation of the equation that I showed before. So we have our F, our drift with bounded with sublinear growth, our sigma, which is our Hölder continuous diffusion, and now we have an additional drift term, which is distributional. Okay. So distributions can be of different types. So the class we work here is the family of Besov distributions. So in particular, we take B to be in a Besov space with regularity B and integrability indices equal to plus infinity. So this is basically a Hölder space, but a negative Hölder space because beta is between -1/2 and 0. Okay, those of you who are familiar with Besov spaces and these type of SDEs with singular drift, we recognize immediately this as the so-called Young regime. Okay, so I will show you something later, but taking beta in this range allows you to make sense of the product between distributions as point products. Okay. All right, so this is the assumption on the distribution. And then we have the usual assumption of the diffusion, the ellipticity. So this is completely unchanged. Now, the assumption of sigma is slightly different. So we're still assuming sigma in a standard Hölder space, in particular bounded functions. The regularity ni, however, needs to satisfy a certain threshold. So the important threshold here is minus beta. So ni has to be greater than minus beta. Okay, so beta is negative, minus beta is positive. So the less regular the drift will be, the more regular the diffusion needs to be. And the upper extreme here is not so relevant. It's just that you don't taking a knee that is bigger than 1 plus beta doesn't allow you to prove better estimates. Okay, so this is the range, the relevant range for the regularity of the diffusion. The intuition, and I'll try to be more clear about this later, is that the regularity of the diffusion has to compensate the fact that the drift is not regular. There's no reason now to take F in a
Sorry, I have a question.
Yeah.
So negative regularity for sigma. So what do you? I know beta is negative. Sorry. Okay.
Negative negative. Yeah.
Sorry. Yeah. Okay. Yeah. Sure. Thanks. Yeah.
Now, there's no reason to take a drift which is a positive Hölder, because all the game will be killed by the drift. So just to keep things not so easy, we like to make things more complicated. We take F in this C0 space, which is, I repeat, the space of basically measurable functions with sublinear growth. Okay, so this is, again, will introduce an extra technicality. Again, in general, we could take diffusion on RD, X valued in RD, and we could have a time dependence on all the coefficients. One thing I forgot to say, this SDE is, it's written, but I didn't say it. You should think about this for the moment, for the time being, today as a formal SDE. So in reality, what we do is we study this differential equation, not by trying to make sense of this drift term pathwise, but we study the singular martingale problem associated to this equation. That will allow us to construct a Markov process on the canonical space. So this is the result, which is broken down in different bits. So the first part is the well-posedness of the martingale problem. So here the concept of martingale problem is slightly different than the classical one. So in the slide, I'm going to try to explain here the precise type of martingale problem that we are considering. So this is not an idea of this of our paper. This is typically how the martingale problem is stated in when, as far as SDEs with distributional drift are concerned. So the idea is that we prove that for any initial time t0 and initial distribution, there exists a unique probability on the canonical space. So the canonical space being the space of continuous functions with the usual Borel sigma algebra induced by the topology of the uniform convergence. And at the initial time, the canonical process, so small x denotes the canonical process. So the canonical process at time 0 is distributed like mu0 under P. Okay, this is okay. The different part, the part that differs from the classical formulation is this. So we want this process M to be a martingale under P. So I'm going to take a minute to describe this. So this process M is defined in terms of this function U, which depends on a function on G and a function L, okay, that are fixed. U is the solution to the Kolmogorov PDE that has G as source term and L as terminal datum. Okay, so if you take a second look at this, so you see G appears here. So if you take a second look at this, this is kind of the other way around compared to the classical formulation where you have a domain, which is typically C2 or C2 with compact support. And then inside here, you have the operator L applied to your test function, to your function f, u, let's say. Okay, but the problem is that if I apply this operator L, L is the generator, okay, so it has a singular part. This B is a distribution. If I apply this to a C2 function, I obtain a distribution. Okay, so I have to invert the domain of the good domain of this operator will be defined by inverting the operator, which is solving the Kolmogorov PDE. So I fix a source term. I need to fix, in order to have a solution of the PDE, a terminal datum, and I obtain a solution. And this, all the U built like this, will form the domain of the operator and will form all the functions that I use to test the martingale property. Okay, so this is quite standard. It's not something novel in the paper I'm presenting. It's the way normally martingale problem is formulated when distributional drift is concerned. Okay, I will come back on this later. This function, the solution to the Kolmogorov PDE will have some regularity. So we'll have some Hölder regularity. Okay, so despite the fact the drift is a distributional, so it has a negative Hölder regularity, the solution will have a positive Hölder regularity. So we'll come back on this later. Okay, continuous in time and Hölder regularity in space. So we prove the well-posedness of this martingale problem, and we prove that, as expected, the canonical process under P enjoys the Markov property. Okay, so it's a Markov process with a semigroup defined exactly by the solutions to the martingale problems once you take a direct delta as an initial distribution. Okay, so this is the probabilistic part of the result. And then, if you want the analytical part, are the heat kernels, so the density estimates. So again, we have Heronson type and regularity bounds. This time I put them all together. Otherwise, it becomes a bit repetitive. Just pay attention to the fact that now the constants lambda, the concentration constant lambda, and the constant C that multiplies everything will also depend on the Besov norm of the distributional drift. So we have the usual Heronson bounds. Okay, this estimate looks exactly like the one I showed before in the non-singular case. And same goes for the estimates, the pointwise estimate on the gradient, exactly as before. And now we see the Hölder regularity of the gradient in the backward variable. Focus now on this blue part, so this regularity index here. So for any eta backward, eta b, that stands for backward, in 0, 1 plus beta, we have Hölder regularity of order eta b for the gradient in the backward variable. Okay, so as usual, you see the structure of this estimate doesn't change. It's exactly as the one in the non-singular case. What changes is the threshold. The threshold here is 1 plus beta. Okay, there's no way you can go to a second order derivative here. Beta is negative. Okay, so the gradient will have Hölder regularity, which is strictly smaller than 1. Okay, and why there's no way of obtaining a second order derivative here? Well, because the worst coefficient is C beta, and the equation regularizes by 2. Okay, so you get to a total regularity, which is of order 2 plus beta, which means in particular that the derivatives with respect to x have regularity 1 plus beta. Okay. And in the forward variables, the threshold, so eta f stands for eta forward, will be the Hölder exponent in the forward variables. And the threshold here remains ni, like before. Okay, because the Fokker-Planck equation will have two derivatives, will put two derivatives on the coefficient, on the diffusion coefficient, which is the less regular term. Okay, so this, if you want, this these regularity bounds could be in a way summarized. Okay, of course, here there's way more information because these bounds are uniform. The Gaussians you have here allow you exactly to have uniform bounds that are not only uniform in time, but also uniform in space. So here, these estimates are very informative, but if you want, the takeaway message could be this. So in the backward variable, the density, the transition density, is of class C2 plus beta. Always minus, because we can get close to 2 plus beta, but not exactly 2 plus beta. And in the forward variable, we have regularity ni minus. Okay. Now recall that ni belongs to this range. Okay. So from here, you can see that when ni is, ni cannot be smaller than minus beta, but when it gets closer to 1 plus beta, basically you obtain C1 plus beta regularity in the forward variable, okay? And this is because this one here kills the additional derivative that the Fokker-Planck equation puts on the diffusion coefficient. Okay, so in order to have regularity of order 1 plus beta in the forward variable, you need the diffusion coefficient to have regularity 1 plus beta. Okay, this is in accordance with the previous results for Fokker-Planck equations with distributional drift in the case of additive noise. When in previous works that deal not with density estimates, but with Schauder estimates for Kolmogorov and Fokker-Planck PDEs with distributional drift, the regularity you end up with for Fokker-Planck PDE is 1 plus beta. Okay, in that case, in those results, the coefficient, the diffusion coefficient is constant. Okay, it's additive noise. All right, so this is the result. So a few remarks and comparisons. So, well, the first thing is that to the best of our knowledge, this is from the point of view of the well-posedness, the weak well-posedness of the SDE. This is the first result for multiplicative noise. So there are by now many results in the literature for distributional drift, but they all concern, to the best of our knowledge, additive noise. So if you want to, this is a very incomplete list. So some early results in dimension 1 can be found in these inceptional papers, the beginning of the years 2000. Some more recent results deal with multidimensional diffusions, and sometimes also driven by stable processes, so Levy processes. So here, sorry, this is a bit mixed up. I think the paper where Lévy processes are concerned is the one by Chedrude, Reynal, and Menozzi. So I have to fix this. Also, well-posedness for degenerate noise has been proved recently. So this is a recent contribution of Elena Soglio, Francesco Russo, Davide Trevisani, and I. Oops, sorry, jumped. And whereas the second one, this one here, this is a case that encompasses as well the para-controlled setting. So the setting which is not young anymore, when the beta is allowed to be even smaller than -1/2. Okay, then there are many other results in the case of additive noise. This is a very incomplete list. When it comes to heat kernels, singular heat kernels, the only result we could compare with this is, of course, at the best of our knowledge, is this paper by Perkowski and Van Zuljen. So basically, in this paper by 2022, they proved Aronson type bounds and the estimate for the gradient. So the uniform estimate for the gradient, of course, gradient with respect to the backward variables. The setting is slightly different due to the techniques they use. For them, it's more convenient to work with a base of space where the Q is equal to 1, the Q index is equal to 1, whereas we work in basically in a negative Hölder space. And also there is no there is no unbounded drift F. Okay, so one can avoid the whole business with the flows associated to the unbounded drift. Now, before we skip to the ideas behind the proof, this is a corollary, a straightforward corollary from the result. So the lower Gaussian bounds give you that the diffusion given by the canonical process and the measure P is irreducible. Okay. Moreover, the regularity in the backward variable gives you the Feller property. So it tells you that this diffusion has a Feller semigroup. Okay, so this means that if an invariant measure distribution exists, this is unique. Okay, this is a classical result. So
you mean strong Feller?
Strong Feller, exactly.
Strong Feller, yeah.
Yes.
Thanks.
Yes. So that means that if you are ever concerned with studying the ergodicity of a diffusion with this type of drift, with this distributional perturbation, all you have to be concerned with is the existence of the invariance distribution, because thanks to these results, you have automatically the uniqueness. Okay, now we take a few minutes to see the ideas behind the proof. So it was clear, hopefully, I hope it was clear from the way I tried to explain the singular martingale problem, that a key role is played by the Kolmogorov equation. The Kolmogorov equation here is very pivotal. So before I show you the scheme of the proof for well-posedness and density estimates, I will have to talk a little bit of how we solve the Kolmogorov PDE. So the Kolmogorov PDE here, it's rewritten. It's basically the equation that was written in the previous slide. The operator is the generator of our formal SDE. It's convenient to break it down into two parts. The K, which is the generator of the non-singular SDE, so drift, which is a function, plus diffusion, plus derivative in time. And the red part, which is the singular first order term. Okay, here I put this dot here because this will be actually a product between distributions. Okay, so it will be this will be a point product, and it's b times the gradient in the x variable. Okay, so as I said before, there is no reason to expect here regularity which is near C2. So we need a weaker, for sure, weaker notions of solutions than classical. In particular, the notion of solution that seems to really fit this framework is the one of mild solution. So mild solution means basically Duhamel principle. Okay, so we seek functions u, so not distributions, functions that can be written like this. So a semigroup, the blue one here, Pf sigma, which is the semigroup of the non-singular Kolmogorov operator applied to the initial datum, plus a time convolution of the non-singular semigroup applied to the source term. So you see the singular term here ends up in the source. What I'm doing here, I'm taking the red part and moving it on the right-hand side of the equality. Okay, so this becomes a source term and it goes inside the time convolution. Okay, those of you who are familiar with the way you represent, for instance, PDEs, solutions in terms, so solutions to Cauchy problems in terms of convolutions with respect to fundamental solutions should find this representation quite familiar. Okay, so there's a slight problem here. What about this semigroup? So, as I said, this semigroup will be applied to a distribution. So, in the case of additive noise, this is quite simple to make sense of this because the semigroup becomes the heat semigroup, and the heat semigroup regularizes infinitely many times. Okay, so basically you can put here any distribution, any temporal distribution you want. And you can define this operator applied to a distribution by dual pairing. So here we don't have dual pairing because the kernel that defines the semigroup is not smooth. We saw it before in the previous results that I reviewed with you. So the kernel of the non-singular SDE has only regularity up to C2, not even, in the backward variable, and only Hölder regularity between 0 and 1 in the forward variable. So we need first of all to define how this semigroup acts on distributions in Besov spaces. And what are the thresholds? How irregular can a Besov distribution be to be fed into this semigroup? And so this is basically the result that allows to define the semigroup. I call it here proposition/definition because so basically this definition entails that you have to prove the existence of a limit. So basically for any phi in a Besov space C alpha, alpha here has to be, here you see the threshold. Alpha has to be greater than minus ni. Remember that ni was the regularity of the diffusion, okay? So ni positive, alpha can be negative, but not too much, okay? The higher the regularity of the diffusion, the more irregular can be the phi here. And so the semigroup is defined as an operator that maps C alpha into this intersection. So basically, the semigroup applied to phi will be C gamma regular for any gamma smaller than 2, okay? And it is defined as a limit in this way. So you take any Of course, the limit is independent on the choice of the sequence, but you take any sequence phi n that converges to C alpha, any smooth sequence, then okay, P applied to the smooth function is well defined simply via convolution. And then you can show that there is a limit in the space in C2 minus epsilon for any positive epsilon. Okay, so by proving this limit, you can define the semigroup of the non-singular kernel. Okay, so this trouble comes from the fact that we have additive noise, which is not smooth. The sigma is not smooth, and neither the f. This is a difference compared to the additive noise world. Okay, now another ingredient is the Schauder, is given by the Schauder estimates. So Schauder estimates the usual. So when you want to, you apply your semigroup to a distribution of order alpha, you can prove C gamma regularity with gamma bigger than alpha, but you pay singularity, which is gamma minus alpha over 2. That's the weight of the singularity. And the theorem here that we needed is so the well-posedness or the Kolmogorov PD, which goes like this. So if you have a source term, which is C beta, like the regularity of the drift coefficient, sufficiently regular initial datum. This is for simplicity. We could go lower than this, but that's enough for our purposes. Then there exists a unique solution of class C2 plus beta, see, in to the Kolmogorov PD. Okay, remember this is the regularity we observed in the backward variable for the density. Okay, so as expected, the regularity will be 2 plus beta. So this result kind of extends some previous results in the literature for additive noise, as I said. And it's also important for what we have to do next to have some stability. By stability here, I mean the following. If you take regularized coefficients, B, so regularized B and regularized source term, again, here B, N, and Gn are modifications, so they're smooth approximation of B and G respectively. So there must be approximations in the space C beta, so in the negative space C beta. Then the solution to the regularized PDE UN converges to the solution of the singular PDE U in the correct space, C2 plus beta. Okay, stability. We need stability because of the way we will approach the existence of the solution to the martingale problem. Okay, so these are the preliminary PDE results that we had to establish here. In particular, oh yeah, this is important. Then after for tightness, the family of the modified solution of the regularized solutions is uniformly equicontinuous in time. This comes exactly from this result because this implies uniform convergence. Okay, and therefore you have equicontinuity. So in this slide, I try to summarize the strategy to prove well-posedness. So the strategy goes like this. You have consider the regularized martingale problem, which means we take as coefficient here the regularized drift. So now B with N is a function that will converge to B in the sense of distributions in the space C beta. We prove tightness for this family, and here we use the PD the properties of the solution to the PD. We use the usual Zvonkin transform. Okay, this is standard. This is a very well-known way of proceeding. So we consider Zvonkin transform, and we take advantage of the gradient estimates for the solution to the Kolmogorov PD and the stability result. And also the equicontinuity to deal with the time variable. So it's important here to see that with respect to time, we have no regularity. We haven't proved any Holder regularity in time. We can do everything simply with equicontinuity in time. This tells us that Pn will tend to some P, but thanks to tightness, we know there is a limit up to some subsequence, but then we also have the identification of the limit. Okay, the identification of the limit, you have to show that any limit will solve the singular martingale problem. And thanks to stability of the Kolmogorov PD, we will get existence. So we will get existence naturally as the limit of solutions to mollified martingale problems. Uniqueness in this setting is quite standard, because first you prove uniqueness for the time marginals using the existence of the Kolmogorov PD, and then you pass, as usual, from uniqueness of the time marginals to the uniqueness of the finite dimensional marginals. Okay, and this gives you uniqueness. So in the end, I want to stress again that the solution P is obtained as a limit of Struck-Varandan martingale problems. Okay, because the mollified martingale problem can be proved reduces to a Struck-Varandan martingale problem. So this kind of gives you some consistency to the whole procedure, and in particular, it allows you quite easily to show the Markov property. Okay, we can now go quickly to the proof of the estimates, and then I think I will skip the part of the generate noise because it's pretty late. So proof of the heat kernel estimates. So this may be interesting for people who are specialists of the parametric expansion, like Andrea, Antonello, Nufel, or anyone else in the audience who's a specialist about this. So the first attempt here was going to be to try the full parametric expansion, which is basically, you represent your P as a parametrics, a Levy parametrics. The Levy parametrics is basically the fundamental solution of the operator with frozen noise. And then you represent it again via Duhamel principle. You have a reminder, which is a time convolution. Sorry, here there's an integration in space missing that I forgot. The integral in space with respect to the z of the parametrics against a series. So the series is basically the reminder. And when you control the series, so normally you would have to control all the terms of the series. And here the regularity is not really a problem, because we're not trying to prove eventually a bound for the second order derivatives. But what is the problem? It comes from the fact that we have the flow associated to the unbounded drift F. So this, combined with the presence of the distributional drift, gives us an explosion of the concentration constants. Okay, I think actually this happens even without the distributional drift, if I'm not wrong. And this explosion forces you to change technique. Okay, you could complete your standard full parametrics construction maybe if F was bounded. So we need the second attempt, successful one, is to use regularization plus one-step parametrics, which means we regularize everything, all the coefficients, in particular the distributional one. We write Duhamel formula use Duhamel principle. And when we use Duhamel principle, we obtain this characterization, this representation of the regularized density. And then we bound uniformly in all variables this function h. Okay. So you see here, this is some sort of normalization. We have the term we want to bound divided by the density of the non-singular SD. So basically, we're going to obtain bounds with this technique by means of the density of the equation without drift. Okay. So this approach strongly relies on the estimates I showed you, I reviewed with you before for non-singular SDs. Okay, and this is it. And then once you have these bounds, you can apply your Arzelà-Ascoli theorem and pass to the limit. Okay. Of course, here it's important that the limit has already been identified. Okay, this is an important thing. So we kind of need the probabilistic part even to prove the analytical estimates. Okay, then there's just a word on the degenerate noise. As I said, the results in reality in the paper are proved for the case of an equation with degenerate noise, where you have a second component which only has drift. As many of you know, the distance, the geometry changes, is no longer the Euclidean geometry, so you have to replace the Euclidean distance with an anisotropic distance and consider suitable anisotropic spaces. Okay. With these changes, the results is pretty much, in the non-degenerate case, in the degenerate case, it's pretty much the same. And of course, you can consider, as particular cases, kinetic models, like for instance, the Langevin model, the early 20th century, that describes the evolution and the position and velocity and position of a particle with subject to random acceleration. Okay, there's no time to talk about this. I prefer to focus on the aspect related to the singular drift. Future developments, I haven't talked about time regularity, the actual dynamics of the process, and asymptotic expansions that could be derived starting from these bounds. And this is subject to ongoing and future investigations. And I think it's 5 sharp, 6 sharp. I'm going to stop here. And thank you very much for the attention.
Thank you very much for your talk. Very nice. Anybody would like to ask some questions? Could you highlight the difficulties coming from multiplicative noise, and especially when you assume that sigma is just a Hölder coefficient, right? So this will actually add a lot of difficulties even for the Kolmogorov PDE, right?
Yeah, exactly. So because you see, you can see it here, right? Because as I said, this will be a distribution, and this will be in C beta, because B is in C beta. Here you have a point product. So you have B times something that is beta plus 1 Hölder. So the sum of the two is B1 plus 2 beta. But beta is greater than minus 1/2. So you're still positive. You're still in the Young regime. You're still in the Young regime. But the outcome is something of this product is something that is beta with beta possibly minus 1/2 or close to minus 1/2. This means that here this semigroup of the non-linear, of the non-singular, the semigroup associated to this operator needs to take in something that could be up to C minus C beta.
Mm.
Okay, but in order for the semigroup of this, here there's a multiplicative noise. In order for the semigroup of K to take in something that is C beta, you need the diffusion coefficient to be C minus beta.
Mm.
Okay. And this is the content of this was a bit fast, but you see,
Mm.
in order to feed a distribution in C alpha to the semigroup, you need alpha to be greater than minus ni. Ni is the regularity of the diffusion. So when you take the extreme case when ni is equal to minus beta, you get alpha greater than beta.
Mm.
So you need some regularity in the diffusion to make sure that this to kill the not to kill. You need some regularity in the diffusion to have a semigroup that is well defined on C beta. Okay. With additive noise, you don't see this because the sigma is a constant,
Mm.
and the semigroup of K is the heat semigroup. So you just heat semigroup regularizes infinitely many times.
I have one more, a bit more controversial question.
Mm-hmm.
So what can you do if you use the whole machinery of stochastic sewing? Does it apply at all for this Young regime for your B?
I don't know.
So
I don't know.
are there more questions?
I have one,
Mm-hmm.
if I may.
Hi,
I
go
know
ahead.
that one of your research interest is a numerical approximation of such dynamics. So, how would you proceed to approximate such SDEs?
Sorry, could you repeat? I didn't understand exactly the question because your voice
So the question is
broke down.
is regarding the numerical approximation of such dynamics.
Regarding, sorry, the approximation.
The numerical approximation, yes.
Okay. The numerical approximation.
So I know that you are interested in this type of questions in the past. So have you thought about it?
Yes. So in the past, exactly. So these type of bounds are like needed if you want to prove when you work with, for instance, asymptotic expansions of the density. You need a priori bounds of this type. And what I would like to investigate now is if some asymptotic expansions, analytical asymptotic expansions for the density could be done in this setting. Of course, it's not at all obvious because in the Holder setting, you would expand, let's say, the coefficients for instance, with Taylor expansion up to some as much as you can. So you would take advantage of all the regularity you have on the coefficients. And then you would prove an asymptotic expansion that can be as whose asymptotic rate of convergence is as fast as the regularity of the coefficients. Here you have no regularity in the coefficients. However, you have bounds that are the same as those that you have with non-singular drift. So the idea would be to try to come up with some asymptotic expansion that is kind of a counterpart to the stochastic simulation, the method that you, for instance, that you and Stéphane work on, which entail discretization schemes for the stochastic dynamics. And also, there's also another aspect which is more connected to this, the standard Euler-Maruyama simulation, discrete time discretization, but would require first the study of the dynamics, because if you want to come up with a numerical scheme, and Stéphane, but also Elena Soglio and other people are working on this in the for SDEs with distributional drift, you first have to characterize the dynamics, and then you start working on the discretization of the dynamics. But here, in the case of multiplicative noise, we haven't studied the dynamics yet. So in order to set up something numerical in the sense of time-stepping methods for SDEs, first we would need to perform the study of the dynamics. That would be a precondition. You can't do it without.
Okay, thanks.
You're welcome.